So in the previous discussion, we were discussing about Wien's displacement law. Okay. So the Wien's displacement law is nothing but your lambda n into t is equal to constant, right? So uh, we had drawn the curve, and we had one like this. Then we have another curve like this, and then we have another curve like this, and these are for different temperature. Okay, so let us say this is your electric ball or tungsten filament. Okay, filament. Okay, and then let us say this is your welding arc, and let us say this is your sun. Okay, so these are at three different temperatures. Okay, so one is 2000, one is 3000, one is 6000. So your sun is at 6000 Kelvin, that's its temperature, and then this is your welding arc, it is at 3000 Kelvin, and let us say this is your 2000 Kelvin, which is your tungsten ball. Okay, so this side you have the wavelength. Okay, wavelength. Okay, and this time this is energy intensity or whatever, energy intensity, let us say. So with this, what we observe that the maximum wavelength, so the maximum with increase in temperature, the maximum wavelength decreases, right? So it is shifting towards left, right?
Yeah.
Okay, so from this curve, the interpretation is that lambda m is inversely proportional to absolute temperature. So that's why lambda m into T is equal to constant. So this constant is otherwise called as Wien's constant. So Wien's constant. Okay. So this Wien's constant value, it will normally be given. Okay. So the value of Wien's constant is like 2.9 into 10 to the power minus 3. So which is equal to 2.9 into 10 to the power minus 3
Kelvin
meter Kelvin. Okay, it is because lambda has unit of meter and T has unit of this thing. So this wavelength normally it is not meter, it will be in angstrom. Okay, so normally it will be 10 to the power minus 9 meter. Okay, so but unit you have to write it in SI unit, so that's is meter. So the value will be 2.9 into 10 to the power minus 3 meter Kelvin. Okay, so with the help of Wien's displacement law, where it is being used. Okay, so this is being used to find out the surface temperature of celestial bodies like your sun, moon, and stars. Okay, so let us try to solve. Let us try to find out the temperature of moon. Okay, so it is being given that so from experiment it has been found that the moon is found to have a maximum intensity near wavelength 14 micrometer. Okay, so for moon the maximum wavelength is where you get the maximum intensity, that was found to be 14 micrometer. Okay, 14 micrometer. Okay, so micrometer, what does it mean? So that is nothing but 14 into 10 to the power minus 6 meter. Okay, so now you know lambda m into T is equal to, let us say, 2.9 into 10 to the power minus 3. So now you know lambda m, that is from experiment, and this is a constant, universal constant. So knowing these two, so temperature of moon is equal to 2.9 into 10 to the power minus 3. Then this micrometer, 10 to the power minus 6 you have to multiply. So 14 into 10 to the power minus 6. Okay. So when it goes up, it will become 10 to the power 3, right? So 10 to the power 3 means it will be kind of T of moon is equal to 2900 that divided by 14. Okay, which comes out to be say 200 Kelvin. Okay, something like 14 into 200, so 200 Kelvin. So So the temperature of moon is around 200 Kelvin, which is around 27 degree centigrade. Okay, so this is how you find the temperature of moon. Okay, similarly, how to find the temperature of sun. Okay, so your sun, that maximum wavelength is found to be 4753 angstrom. Okay, so this is for sun. So let us solve it for sun. Okay, so that lambda m is equal to 4753 angstrom. Okay, which is nothing but 4753 10 to the power minus 9 meter. Right. So knowing this, so now you can solve like say 4753 into 10 to the power minus 9 into temperature of sun is equal to 2.9 into 10 to the power minus 3. Okay. So you have one unknown, and if you solve this equation, you will find the temperature of sun to be 60. So the temperature of sun is 60 Kelvin. So 6060 Kelvin. Okay. So this is the temperature of surface of sun. So but it is not the temperature of interior of sun. So temperature of interior of sun is much higher. Okay. So this is an important application of Wien's displacement law, and how we measure the temperature of celestial bodies like sun, moon or any other star, because we know the Wien's constant. If we can get the wavelength at which the intensity of radiation is highest, then using that wavelength you can find out the temperature of the body. Okay. So these are all related to radiation. So we have discussed conduction, we have discussed convection. So this is the details, complex numerical problems of convections. Normally it will be forced convection. There will be many more complex numericals which is not in the scope of your 12th. Okay. So when we study engineering, like say chemical engineering or mechanical engineering, there this heat transfer is a very important subject. Okay. Chemical engineer study heat transfer, mass transfer both. Mechanical engineer study your heat transfer. Okay. Why we need heat transfer? Suppose you want to design your car radiator and all. So there is a heat transfer happening. You are pouring some water there. So it flows through the zigzag path, and it takes away the heat from the engine. So if the engine will be cooler if you take away heat using the radiator, which is otherwise called a heat exchanger. Okay. So the water has more heat capacity or the latent heat. So if that water will take away the heat from the engine. That is, so those kind of design of a heat exchanger or radiator and all those things, it is very important to understand heat transfer. Okay, that is convection. Conduction, like say iron rod, I am heating it at one point. What will be the temperature at any location? That is also an important thing in designing various structures, okay, which are subjected to thermal environment. Okay. So yeah, take a picture of it. Okay, so next related to radiation is your Stefan Boltzmann law, and related to in like Wien's displacement law. Related to Stefan Boltzmann law, you will get many numericals in your JEE or your entrance examinations. Okay. So what is Stefan Boltzmann law? Okay. Stefan Boltzmann law. Boltzmann law. Okay. So energy can be transferred by radiation over long distances without a medium. In vacuum also it can. The total electromagnetic energy radiated by a body at absolute temperature T is proportional to its size, its ability to radiate, and most importantly temperature. So in radiation, amount of heat radiated depends on what are the things. It depends. Okay. Suppose let me see, I have a sphere. Okay. So I have a sphere. Okay. So if I have a sphere, okay, so this sphere will have a cross-sectional area, surface area 4 pi r square. So volume is 4 by 3 pi r cube, surface area is 4 pi r square, right?
Yeah.
4 pi r square is the surface area. So this sphere, let us say this sphere surface temperature is capital T. The surface temperature of the sphere is capital T, and let us say this sphere is not a black body. It will have some emissivity. Black body will have maximum emissivity, which is equal to 1. But any other body, it will have some emissivity. Let us say that emissivity of this body, this surface is, let us say, E. Okay. So, so this is 4 pi r square is nothing but its surface area, right? So, the amount of heat radiated, okay. So the amount of heat radiated is directly proportional to surface area, directly proportional to absolute temperature, and directly proportional to emissivity. Okay, so all these things. So it is here is the catch. It is not directly proportional to temperature. It is temperature 4. Okay, so the amount of heat radiated so because this is proportional to these three things, so you can write as H is equal to directly proportional to E A T4, right? So this is the equation. So if you want to put a equal to sign, you have to write the proportionality constant, which is sigma, which is otherwise called as Stefan Boltzmann constant. Okay, sigma emissivity A into T4. Okay, so this is the Stefan Boltzmann equation. Okay, so this is your Stefan Boltzmann equation. So this value Stefan Boltzmann, this sigma, there can be a question, what is the unit of sigma, right? So so this H is actually, it is heat this is actually heat flow rate. Okay, rate. So it is watt only, joule per second already. Okay, this H can also be, it is otherwise Q dot also, means heat flow rate, not heat flow. Okay, so there can be a question, what is the unit of sigma? So it will be H divided by E A T4, right? So this H has a unit watt or joule per second, whatever you want to write. So it will be watt divided by area, you can say meter square, and T4 is Kelvin 4. Okay, so watt meter to the power minus 2, Kelvin to the power minus 4. So this is the unit of Stefan Boltzmann constant. And like Wend's constant, there is a value of the Stefan Boltzmann constant, which is, so the value of sigma, is 5.67 into 10 to the power minus 8. 5.67 into 10 to the power minus 8. 10 to the power minus 8. Okay, 5.67 into 10 to the power 8. Then unit is watt meter to the power minus 2, Kelvin to the power minus 4. So this value also you remember. This can be a tricky question. Okay, so 5.67 into 10 to the minus 8 is the Stefan Boltzmann constant. Okay, that we need to remember. Okay, so the general conclusion is, most bodies emit only a fraction of rate given by this. So if this is the rate, so because of E, most bodies which are not black bodies, they will emit fraction of it. Okay, So, but a substance like lamp black, which is a pure black body, okay, this will become 1, okay. So, uh, this E value, E is a dimensionless value, and E is equal to 1 for a perfect radiator. Okay. So, okay. So we'll try to use what is the so take a picture. Then we'll solve a numerical related to this with the real world application. Okay. So let us say I have a lamp. Okay. So I have my tungsten lamp. Say. So I have a like say. Uh, so I have my this lamp. Okay. So I have this tungsten filament, and let us say this is my folder or whatever. Okay. So this is my lamp. Okay. So I have a tungsten lamp whose emissivity is about zero point 0.4. So this tungsten filament, this lamp has a emissivity, the outside surface. Okay. So this lamp surface has an emissivity E is equal to 0.4 because it is not a black body. Okay. This tungsten lamp at temperature 3000 Kelvin. Okay. So so the lamp has a temperature T is equal to 3000 Kelvin. Okay. Okay. So we want to find out how much heat it is radiating. That is our purpose. Okay. So how to find it out? Huh? And the surface area of this lamp. So area of this lamp, the surface area is equal to 0.3 centimeter square. Okay. 0.3 centimeter square. Okay. So these things. If this is the thing, then how much, the question is how much heat will be radiated by this bulb. Okay. The question, how much heat will be radiated by the bulb. That's the question. Okay. So that is nothing but your Q dot or H, whatever you want to write. Then E sigma A T to the power 4. Right? So this will be 0.4 into area, you can write 0.3 into 10 to the power minus 4 meter square, because cm square you are converting into meter square. Okay, so 0.3 into 10 to the power minus 4. Then emissivity, your emissivity is 0.4. Okay, 0.4 and this. Then 5.67 into 10 to the power minus 8. That is the sigma value. Okay, 5.67 into 10 to the power minus 8. That's your sigma value. And then your temperature. Okay, which is 3000 Kelvin. 3000 to the power 4. Okay, so that is your heat flow rate. Okay, that will be in watt. Okay, so by solving this equation, you will get how much heat that is being radiated. Okay, so this, if we solve it, you will find it to be 60 watt. 60 watt. So that's why. So this bulb radiates 60 watt of heat. Okay, so the wattage can be calculated based on current I square R also. Okay, I square R or V square by R. That is one way. Okay. Another way is how much heat is getting radiated. So this particular bulb with this kind of surface temperature, emissivity and area radiates 60 watt of heat. Okay. So this is one important application of this is an important application of Stefan Boltzmann law. These are all related to radiation. Okay. And then we'll try, you take a picture, we'll solve one more real world example. Related to Stefan Boltzmann law. Okay. So this is a direct equation. Suppose your body, suppose my body is here. So my body is at temperature T. Okay. My surrounding, so I have the surrounding. Okay. So this surrounding is at, let us say, temperature Ts. Okay. So there will be a heat transfer between these two. This will be giving it, this will be giving it. So there will be the net heat. What is the net heat? So that net heat formula will be like Q dot your H is equal to E A sigma T4 minus Ts4. Right. So this is the net heat. Okay. So let us try to solve one real world example like our human body. How much heat we are radiating and all. Okay. So for example, let us estimate the heat radiated by our body. Okay. So let us say I have like say this kind of this. Okay. So like say I have this human. Okay. So let us say the area of our body, is, let us say 1.9 meters square. Okay. So I have a human whose area of the body is 1.9 meters square. The yeah. So the skin temperature is 28 degrees centigrade. Okay. So the skin temperature. Okay. So skin temperature, our skin temperature. I see skin temperature is 27 degrees centigrade. Okay. Sorry, 28 degrees centigrade. 28 degrees centigrade. So don't confuse skin temperature with our internal body temperature. See, our body temperature will always be in that range, 37 degree, 36 degree. That is the normal temperature. That is the internal temperature. But we have to consider the skin temperature here, not the internal temperature. Okay, so maybe this internal temperature may be 37. But the skin temperature is 28. Okay. So the question is how much heat a human is radiating. Okay. So A we know, sigma we know. Okay. And temperature also we know. Okay. Then
sigma we don't know.
Sigma is given na Stefan Boltzmann constant. Okay.
Emissivity we don't know. Sigma we know emissivity.
Emissivity. Okay. So it is given that emissivity of skin. So E skin is equal to 0.97. Okay. 0.97 they have given. Okay. So with all this, we can find out how much heat is being radiated. The net heat. Okay. So the net heat. So net heat is equal to your let us say your net heat is equal to E is equal to 0.97, then your area is equal to 1.9, and then your sigma, which is we had done it earlier, which is 5.67 into 10 to the minus 8. So your sigma is 5.67 into 10 to the minus 8, and
temperature is 28.
So
we have to convert that.
So it is watt per meter square. So watt meter to the Kelvin to the minus 4. So this is your sigma value. Okay. So 5.67 into 10 to the minus 8. This is your sigma. Then your body temperature is 28, which is equal to 273 plus 28 is equal to 301 Kelvin. Okay. And the surrounding temperature, it is a winter, and the surrounding temperature is 22 degrees. So Ts is equal to 22 degrees centigrade, which is equal to 22 plus 273 is equal to 295 Kelvin. Right?
Yeah.
So by replacing this 301 to the power 4 minus 295 to the power
Four.
4. So by solving this you will find it to be 66.4 watt. 66.4 watt. So this much of heat our human body is radiating. Okay. So which is more than half the rate of energy produced by our body at rest. Okay. So our body produce like the when burning of what happens, the oxygen burns the carbohydrate.
Yeah.
So that reaction, with that reaction you are producing for every second 120 joule. So 120 watt you are producing. Out of that, because of the colder temperature and all, this much of heat is getting radiated to the surrounding. Okay. So to prevent this heat loss effectively, so better than ordinary clothing, like say, as compared to the ordinary clothing, if you want to reduce the radiation of heat to the outside, you put a shiny metallic layer next to our skin, which reflects the body's radiation. So if you have a inside your dress, if you have a metallic layer, instead of allowing it to go out, it will
stay inside.
prevent and it will reflect it back, so that your heat loss will be less. Okay. So this is all about Stefan Boltzmann. Okay. Okay. You have taken picture. Okay. So huh? Already you have taken.
Yes. I took from him.
Okay, fine. So this is your Stefan Boltzmann, and based on this there are many numericals that can come in your this thing. You just have to remember this. Okay. So other than Stefan Boltzmann, there is another important concept that is called your Newton's law of cooling. Okay. So we will do some numericals on that. Just I will introduce you to Newton's law of cooling. Okay. So Newton's law of cooling. These are all related to radiation. Okay.
Yeah.
Newton's law of cooling. Okay. So the governing equation of Newton's law of cooling is like this. So let us say your body is at temperature T2. Okay. It is getting cooled to temperature T1. Okay. So the average temperature, so the question they will ask is how much is the time taken for when the surrounding temperature is this much, how much is the time taken, let us say the surrounding temperature is 20 degree, okay, and you have some water at 80 and it will get cooled to 60. So how much is the time taken? That kind of questions will be asked. Okay, so let us say that T2, let us say this is that 80. Okay, and let us say this is that T1, which is that 60, let us say, and let us say this surrounding temperature is, let us say, 20, right? So this is surrounding temperature. Okay, so it is being written like this. So T2 minus T1 divided by the time taken. Okay, so this is time taken. Okay, you can write it as small t or del t, del small t, which is the time taken. Okay, so T2 minus T1 by delta t, which is the time taken, is equal to your let us say there is something called a constant. Okay, so there is a constant into T average minus T surrounding. Okay, so this is the equation. Okay, so this K value they will be giving
Constant.
So T2 say T let us say T2 is the initial temperature and T1 is the final temperature. So 80 to 60 it is becoming, or you can say that T1 is 80. Okay, T1 and T2. Right. So
T1 minus T2.
T1 minus T2 is equal to by time is equal to K, which is otherwise called this. So this K. So it's a positive constant depending on the area and nature of surface. So this K is nothing but a constant. So K is a constant. Okay. Okay. So this is the relationship, and if you like say if you draw a graph between, let us say in the x-axis it is time, the time taken t, and let us say in y-axis this temperature will decrease in a this will be a logarithmic this thing, logarithmic way. So initially the rate of decrease of temperature will be very high because the slope is very high, but slowly it will be, the rate of cooling will be, the temperature drop, the slowly it will be flattening out. Okay, so so this we can say that like say it is something like this. So let us say this is my theta 0. Okay, the initial temperature, say theta I, and this is your the final temperature. Okay, so theta I to theta 0 when it cools, and this is how the curve looks like. Okay, so initially the cooling will be faster, and then so theta 0 is the atmospheric temperature.
Yeah.
So initial temperature to atmospheric pressure temperature when it cools down, it will be kind of a logarithmic curve.
Yeah.
Okay, the curve will be looking like this. Okay, so we can do one numerical. One numerical will do one Newton's law of cooling. So let us do that numerical because we are deriving it now. Let us do that numerical quickly. Okay, so yeah, so the numerical is like this. It is one J question. Okay, so let us put it here this side like this. So minus k into T average minus T surrounding, I have told. Okay. So the question is like this: hot food cools from 94 degree to 86 degree centigrade in 2 minutes. Okay. The question is hot food cools from 94 degree to 86 degree, 94 degree centigrade to 86 degree centigrade in 2 minutes. Okay, in 2 minutes. Okay, then next part is how long it will take for cooling the food from 71 to 69. So how long it will take for cooling the food from 71 degree to 69. Okay. So almost in every JEE paper this type of questions are coming. Okay, if you know the time interval for one cooling, how much will be the time interval for another this thing. Okay, so you can write it like this. In the first case, say it is from 94 to 86, right?
Yeah.
Okay, so 94 to 86, and the surrounding temperature it is being given. How much is it? 28, na? So how much is the surrounding temperature? 20. Huh. The room temperature is 20. Okay, so here room temperature.
TS.
Okay, room temperature, that is the TS. The surrounding temperature is 20 degrees centigrade. Okay, that is also given. So 94 to 86. So that means this is T1, this is T2.
T2.
Okay, so if I use this equation here, so 94 minus 86, and how much time it takes? 2 minutes, right? 2 minutes is equal to the average temperature. So what is the average temperature? So 90, right?
Yeah.
94 plus 86 by 2 is equal to 90. 99. Yeah. So is equal to minus K into 90 minus
20.
20, right?
Yeah.
So be careful, let us convert it into Kelvin, okay? Because it is T only, so let us convert it into Kelvin and then do, okay? So 273 plus 94 is nothing but 268, right?
360.
Sorry, 273 plus 94, 373 minus 6 is 367. So 367, and then this is just this is how much more than that? How much less?
359.
8 less, na? 8 less.
359.
359 divided by 2 is equal to minus K. This is 373, 363, and this is 293. So this is what is one equation. So this is equation 1.
Okay.
Okay. So this is equation 1. Now the second part of the question is this. Okay. How long it will take for cooling the food from 71 to 69? So the equation 2 will be like this. Say the equation 2. So if we add 71 to 273, it will be 344, right?
Yeah.
So 344 minus 70 plus 273. Okay, this is 342 because this is just 2 degree.
2 degree.
342 divided by, so this time we do not know delta T. How much time it will take, we do not know. And then on the other side it will be again minus K into the average temperature. Okay. So the average temperature of 344 and 342.
Or not,
right?
71 plus 69 will be.
No. Let us. This is 344, 342. So average will be 343 only.
Yeah.
Right. So it is 343. That is the average temperature minus.
Same that.
293. Okay. So now this is your equation 2. Okay. So if you divide equation by, 1 by equation 2, K cancels. You don't need K. Okay.
Find delta.
If you solve this delta T is coming out to be. This delta T is coming out to be. Coming to 0.7 minute. Okay, 0.7 minute. Okay, 0.7 minute, which is equal to 42 seconds. 42 seconds. Okay. So this delta T, sometimes they will write as T also. Okay, T is equal to 2 minutes. Then how much is the T or in other case? So even though it is time taken duration, better to write it as delta T.
Yeah.
So in this case it is delta T1, that is for one interval you can say it is delta T1, other interval it is delta T2, you are finding out delta T2. Okay. So the main thing is you have to remember this equation. Okay, so you have to remember this equation. So if you remember this equation, your job is done. So first just remember T1 minus T2, capital T1 minus capital T2 divided by time duration is equal to minus K into T average.
Minus.
T average minus surrounding temperature. So in the right side surrounding temperature will be there and average of these two values should be there.
Yeah.
There will be a lot of confusion in this.
Yeah.
So I have made it very simple. Okay, T1, T2, then find the average. In the left side you will have T1 minus T2 divided by time taken.
Yeah.
Okay, so there will be definitely a numerical on this. Very simple. See, these numericals on heat transfer and thermodynamics, they are not complex like kinematics and dynamics and all, where you have to break your head like anything. These are simple. It will take lesser time and the formulas are much simpler. Okay. So we have done the numerical on Newton's law of cooling and then the Wien's displacement law. So in the next session we will do some more numericals related to Stefan Boltzmann law, and then with that we might have covered almost all the numericals. Okay.